Hello, BNS 210. Before we get into the F test, I wanted to let you know that I did post up a worksheet for you guys. We will make that due on Thursday, and then we'll do a live class where I'll go over it on Friday. So we'll do that. I'll make it due by noon on Thursday. Let's do that. And then on Friday, I'm going to send out the SPSS quiz and quiz 2. And those will be due. See, last day of class is on the 12th. So let's make it due on Monday by 5. Open note, open book, however you guys want to do that. Okay. So today we are going to, let's do, no, not this one. I want to do this one. All right. Okay, so today for this lecture, I am going to go into the mechanics of the F test. I do want to remind you that we will not be doing any actual calculations by hand, okay? But it's important to know where the numbers are coming from. So I want you to understand this is a concept more than the math. Okay, so I bring us back again to this equation. This is the equation that the t-test uses. This is also the equation that the f-test uses. We've talked about this already when we talked about the t-test, and we talked about this already when we talked about the one-way ANOVAs. So remember again, the systematic variability is the difference between your independent variables. So this is what you have manipulated. So you want that to be high because you want the difference to be due to your manipulation. This does also include systematic error, which are compounds. These are things that you know played into the scenario here. And then here in the denominator, we have our extraneous error, our random error. This is what we cannot avoid because no experiment is perfect. So with this equation, we're going to work this equation out, and ideally you want the numerator to be greater than the denominator. The larger the numerator is, the more likely your data is to be significant. So let's get into this. Okay, so we've looked at the one-way ANOVA, and this is the table that you get. So I've showed you guys some of this already with this. So we've seen this. This is sums of squares, sum of squares for your one-way ANOVA. So here you have your between groups. Again, if we go back to this, you have your between variability in the numerator, and you have your within in the denominator, okay? This is your variability between conditions and your variability within conditions. Okay, so here you have your sums of squares for your between conditions and your sums of squares for your within conditions. We're gonna go through this equation and why this works this way, but if you take the sum of squares and you divide it by your degrees of freedom, you're gonna get this number here, mean square. Then, if you take this sum of squares and you divide it by your degrees of freedom here, which is 95, you're gonna get this number. This right here in your mean square is this equation. Okay, this is your between over your within. So if you were to take this and you were to divide this out, this is your numerator. This is all of the variability. This number represents all of the variability between your conditions. This is your, this is a one-way ANOVA. So this is between all of your levels of your independent variable, your manipulation, and any compounds that might be playing a role. Then this number here is your denominator. This is your extraneous error here. This is just random error here in the denominator. If you were to divide this out, you'd get this number here, 3.461. This is your F value. This is your F statistic. It is this number, and the larger it is, the more likely it is to be significant. And here we have our significance level, our p-value, which is 0.036. So it is significant here. Ideally, and we're going to talk about this in a moment, this F will be larger than 1. That is the goal. Now, okay, so that. Okay, so now I want to talk about the sums of squares in SPSS. I want to talk about where we might find this. Hang on, do I have, yeah, okay, yep, okay. what we're going to be talking about today are factorial designs. We're going to be working with ANOVA and factorial designs. So we're going to work with a 2x4 independent groups factorial. If you're dealing with this, you have two main effects, right? You have a main effect in your variable here, which has 2 levels, and then your independent variable here, which has 4 levels. That's your second main effect A, main effect B, okay? And then you're gonna have an interaction here, okay? So those are 3 hypotheses that the ANOVA is gonna test. Okay, it's an independent groups factorial, so we know that our independent variables here are between subjects variables, right? Okay, so this is the chart that you would get for your SPSS, okay? So let's look at this here. You don't have to worry about this first line. It's all on a slope. If you guys remember like your B squared, I don't really remember the equation, but anyway, this is the intercept of your slope. Anyway, you don't have to worry about this one. But here you have treatment 2 and treatment 1. Treatment 2, you can see by your degrees of freedom that this represents this independent variable here, or 2-level independent variable. Treatment 1, this right here, TX is an abbreviation for treatment, FYI. Right here we have TX1, and as you can see by the degrees of freedom, this represents your independent variable here, your 4-level independent variable. Then here you see, just like we write it here, that this is our interaction. These two are interacting. This is the interaction here. This is this variable interacting with this. And then we have our error term, okay? So when we work this out, here's our sums of squares, and we're gonna talk about where these numbers come from. That's what we're gonna talk about today, is these numbers. How do we get these? Because this is where we're gonna represent the variability. And then we're gonna divide it by our degrees of freedom, okay, to get our mean square number here. Here we have our sums of squares for our second independent variable. So this is main effect 1, main effect 2, and the interaction, okay? And then this is the error term. It's over the random error, okay? So you take this divided by 66, and this is our denominator. So you put this over this. If you divide those out, you get 13.37. That's our F value. If you took this and divided it by this, you would get 0.57. If you took this divided by this, you get 0.43. Notice here that here, this number, this 5,650 is smaller than your denominator. Notice this too, that the interaction term, the mean square is 4,277, and it is smaller than this. And you can see this one, this numerator here for your treatment 2, this one is quite large compared to this. So we could even, I'll just show you. I don't know if I can, do you see that? Yes. Okay, so if we take 132,445.91, okay, and then we divide it, whoops, and then we divide it by 9903.44, you can see we get 13.37. So that is our F value. So that's how we get that, okay? So remember, it's this divided by this, which equals this, and then this over the error term, okay? And you take the error here and you divide it by the degrees of freedom. This represents all of the degrees of freedom here, and that's gonna be your mean square. Okay, so that's what we're talking about today, where these numbers come from. Are we with? Everybody with me? Okay. Okay, so I'm going to work through this by using an example for our analysis of variance. Remember, this is the analysis of variance. Our ANOVA is analyzing the variance of all of these things. Okay, so we're dealing with a factorial design. We are going to have, well, for this, we are going to use the example of our caffeine and water example. We're going to add a level so that it can be appropriate for an ANOVA, so we have a multi-level design here, okay? So here we have our participants, our 3 subjects that are going to drink 12 cups of coffee, and we have what they scored in our reaction time task, smaller numbers representing a faster reaction time. So here we have Barney, Belinda, and Barry. Remember Barry in our arm cast? And then we have our 3 subjects that are going to drink 12 cups of decaf coffee. So we have a placebo here. We have Beth, she has a heart condition. We have Bobby, he has Parkinson's. And then we have Brody, who has a medical marijuana prescription. And then we have our 12 subjects who are going to drink water. We have B with the amphetamine addiction, Beavis, who plays the video games, and Bertha, who has had experience in a reaction time study before. You remember these characters, right? Okay. So we are hoping that whatever we see in our reaction time, that the difference that we see in our reaction time is because we gave our subjects caffeine. This makes sense, right? We want our caffeine group to have a faster reaction time compared to the water because we believe something about caffeine is going to do something to increase our reaction time. Okay, so we want to know how much of this variance is because of our manipulation and how much was due to error. So the first step we have to do is we have to find what's known as the grand mean. So if we take these values for each of our levels of our independent variable, we have 3 subjects in each, and we add these up, divide by 9, we get a grand mean of 14.4. So that's the mean of our entire experiment, okay? The mean of our entire experiment. It's the grand mean. Okay, so here's what that might look like on a graph. Okay, so what I have here is I have our reaction time from 0 to 30 seconds. I have, and you guys can calculate this up, this math is correct. If I take everyone in our caffeine group, our 3 people, I add up their scores, divide by 3, I get an average of 21 for their reaction time for the caffeine group. For our decaf group, if I take all 3 of them, divide, I get 16.6 as the average. For our water group, I get 5.6. So this is within each of our levels of our independent variable. We have a mean of that independent variable, and it varies, and it has its own curve and its own variability, okay? And then here's our grand mean here. Okay, so for our example, I'm gonna take, and you could do this with any subject really, but I'm gonna take Barry because it rhymes with vary, and we're working with the analysis of variance. So first and foremost, Barry, he's the one in the arm cast, he got a 28 on our reaction time task. His score is different, as you can see. It's different from 14.4, so it varies, okay? Barry's score of 28 varies from the grand mean of 14.4. Barry was in the caffeine group, so he was given caffeine. As you can see, Barry's score of 28 also varies from his mean of his group, which is 21. And the mean of his group, 21, varies from the grand mean of 14.4. You guys see all those places where Barry varies, right? Okay, so you don't have to memorize these calculations, but these are the sums of squares calculations. So we have Barry. And if we took his score, he becomes X here, okay? So if we look at the total sums of squares represents our A here. If we took Barry's score, 28, and subtracted the grand mean and squared it, and then we took every single participant in the entire study and did this, the score minus the grand mean, and squared it, and we summed it all up, okay? That would be our total sums of squares. It is the sum of the squared of all of our participants in the study compared to the grand mean. B, this line here, represents our within sums of squares, because somebody varies within their own group because of extraneous error. It's because he's wearing an arm cast, and you didn't kick him out of the study because he was wearing an arm cast, even though when he came in, you were probably like, oh shit, he's gonna be pretty slow, right? So I'll let you guys wonder if what I'm drinking there. So Barry is going to vary from his own group, and everybody else in his group, everybody else that was given caffeine, is also going to vary somewhat from the mean. So what we're going to do is we're going to take his score of 28, we're going to subtract it from 21, and then we're going to square it. And we're going to do that for every single person that was in the caffeine group, okay? and that is going to be the within sums of squares. We're going to do that for all of our participants. Then this here, the between sums of squares, is what is represented by our C. This is caffeine. Caffeine now becomes the mean, okay? So we're going to subtract 21, which is the mean of that individual group. And we're going to subtract it from the grand mean to see if it varies in any kind of meaningful way. So we're going to subtract 21 from 14.4. We're going to square it. We're going to do that for caffeine. We're going to do it for decaf, and we're going to do it for water, okay? We're going to sum it up. This is our sums of squares, okay? So this is our total sums of squares, our within sums of squares, and our between sums of squares. Okay. So that's how variance is expressed in ANOVA. Again, you're not going to have to actually like add this out, but you are going to have to understand where these numbers are coming from, okay? So, this is expressed, our variance is expressed and calculated based on these calculations. So this is how the numbers, this is how sums of squares is derived. This is where these numbers come from. And the ANOVA does all this for you. So again, our between sums of squares, which is determined by our manipulation and error. And then we have our within sums of squares, which is by error only. And this is how we get our F value. Okay. Now, because we're dealing with factorial designs, we're dealing with multiple levels of independent variables, we do have to consider the degrees of freedom. So in order to complete this calculation has to be altered just a little. So that's when we're going to change it just a little, and we're going to divide by the degrees of freedom. So for the sums of squares between, this is the deviation of the mean from the grand mean. And our degrees of freedom here is the number of groups minus 1. No, my battery's running low. I better hurry up. And then for our sums of squares within, this is how any data point varies from their group mean. And this is the number of subjects minus the number of groups. Okay. The larger our F ratio, I've already talked about this, the more likely it is due to the independent variable, and also the more likely we're going to see significance, which is what we want, right? We want our p-value to be less than 0.05 so that we could reject the null hypothesis. Okay, so remember here, we're looking at this. This is what our calculation is, and this is how our equation works. This is our between groups divided by degrees of freedom, which we get the mean square. Then this divided by this, which we get this. If we divide this out, we get our F value. And then again, if we came here, this is our equation here where we have the same thing here. So this is our error term. This is all of our subjects that we had. So this is our random error. And then this is the sums of squares for each individual main effect and then our interaction. This is called type 3 sums of squares. This is just type 3 because it's a factorial design, and all type 3 means is that they calculated the ANOVA, it's not like there's people doing this. This program prioritizes the interaction. Okay, so we got that in before my laptop died. So I hope that makes sense to you guys. I know that was a lot of information. That certainly is a lot to learn in one little PowerPoint. So feel free to ask me questions. I will, of course, be on the message board tomorrow morning, and I'll be here all week. So see you guys.